today I will be talking to you guys about the tropospheric emission monitoring of pollution, TEMPO. And there is a mission that was funded by NASA, and it's already being built and waiting to be launched. And from it, I will segue to introduce a similar mission to the Middle East. So thank you again for inviting me. And what does TEMPO do? So TEMPO was selected by NASA in November 2012 as NASA first Earth Venture Instruments proposals. So the idea is that NASA will provide funding, and in this case for us, $90 million to build the instrument. NASA will provide additionally, separate from that, a launch vehicle, a rocket, and a spacecraft where the instrument will sit on. The principal investigator is Kelly Chance, and I'm one of the co-investigators in the original proposal. On the original proposal, NASA required, and the instrument was developed by Paul Aerospace out of Boulder, Colorado. NASA requires most of the proposal funded by it, or at least this one for the Earth Venture EVI proposals, to have a management center be one of NASA centers. So we are working with our management center is NASA Langley in Hampton, Virginia. Additionally, we collaborating with NASA Goddard Space Flight Center outside DC, and with a group of universities and government agencies in US. We have international cooperation in Korea, Europe, Canada, and Mexico. As I go through this, it will be apparent and understandable how these collaborations come to exist. So again, the instrument was, we won the proposal in 2012. The instrument was built and done, and it's delivered, and it's sitting in Boulder, Colorado right now. That was done in 2018. Earlier this year, earlier in the year, NASA selected host, which is the spacecraft, and the launch vehicle, which I will talk about it later on when we get to it. What TEMPO does, TEMPO is actually measures in UV visible. It has two detectors, which I will talk about in great detail. And it measures the backscattered sunlight. And it measures the intercontinental US. And it can make measurements in for various species. And I should point out that within the American scientific community, and typically American European, they tend to be decadal studies. And in our case, they was called what was called the GeoCape study that actually proposed such a measurement or such an instrument to be built prior to us actually proposing it. So again, it's a geostationary, and let me explain that to you in detail. So if I have here the Earth, as you can see it, and you see one of my colleagues, this is Joe, and he, for whatever reason, we selected him to be the guy where the instrument will be. So TEMPO will be here. This is as far from you, the Earth, as roughly 36 kilometers away. Now, you can put instruments in low Earth orbit, what's called LEO, L-E-O, LEO, and tend to have a sun synchronous orbit, and it will go like this as the Earth is looping around, and the coverage will go. So as the spacecraft coming up and down, the space is going like this. So you could imagine it will have a global coverage. However, that it has global coverage, but the swath as it's coming up and like this is massive. It's hundreds of kilometers, wide. And I will show you this. Now for GEO, you sit, this is Earth, you sit 36,000 miles away, parallel to or along the equator, you're looking at certain geographical area, and as the Earth, rotates, you're following it. So basically you stay focused on the same point. Obviously, disadvantage is there is no global measurement. You're only looking at this piece. However, you're looking at it in higher spatial. distribution. It's in tenth of kilometers, 10 or less kilometers square rather than hundreds. Second, you see more than one measurement per day because you are looking at it. You measure the backscattered sunlight. So as long as there is sun, which could be 16 to 18 hours a day, you are having measurements. But if you are in LEO and you are 600 to maximum 1200 kilometers above Earth, the only thing you will see as Earth rotates, and here you going like this and Earth rotates, say Earth rotates, take for example OMI, or Ozone Monitoring Instrument, which I will talk about, or GOM, Global Ozone Monitoring Experiment. There is 1 and 2 of those were built, and those are ESA, GOM are ESA instruments, OMI are ESA and NASA, ESA European Space Agency. So, but as like for any LEO instrument, as Earth is going around and the spacecraft is going like this, it will see each point in Earth once per day. So for Doha, for example, you will be able to measure once per day, where or Paris once per day, but if you have, or Washington, DC once per day, but if you have one over US, say, you will be measuring Washington, DC 16 to 18 times per day, which will give you different data points. So that's the difference between, between the LEO and GEO. Now, in order for us to cover US, here I am displaying kind of bunch of satellites that's already exist in orbits in geostationary around the Earth. And obviously, if you think about it, your airspace above Qatar or above any country, your geostationary orbit is good for you, meaning Russia cannot come and put the spacecraft in geostationary orbit over US because that's obviously above it. It can put one in LEO, in low Earth orbit. So for us, in order for us to see North America, that's our field of regard, we would like to be here, and we managed NASA to get us 91 West. So we are here, roughly, we're gonna be looking at North America, which fits into the position we would like. Now, who are our partners? As I pointed out, Paul Aerospace in Boulder, Colorado built the instruments. And I will talk about other partners when we come to them, but Maxar here in Palo Alto, California is the one building the spacecraft. And it's going to be managed afterward by Intelsat. And we have the Instrument Operations Center in Cambridge, US. I'm responsible for that, for the whole IUC, the Instrument Operations Center, where there we receive data. The data will come from the spacecraft down to some ground station in Midwest, say, somewhere in the Midwest of US. We will receive this telemetry raw data to the IUC, the Instrument Operations Center, where over there we'll break the data down. NASA defines data as level 0, 1, 2, and 3. So raw data is just raw data that comes out of the spacecraft. Level 0 is you taking the raw data, you time order it and remove the artifacts. That becomes a level 0 data. Then you take level 0 data and it's an engineering unit. You apply physical units to it. So let's say photon per centimeter square per radiant, or Dobson units, or whatever kind of physical unit to give you the physical meaning. And that becomes level 1. I will talk later about level 2 and 3. Then when we finish level 0 data, we send it to the STP, Science Data Processing Center, where that we will take and produce level 1 and 2 and 3 and send it to NASA DAC, which is the NASA archive, also happen to reside in Langley, Virginia. And we can send it to the scientific community as a whole afterward, or they can receive it from the DAC if they prefer. So now, again, as I said, this is Tempo as it was sitting in the clean room in Paul Aerospace. This is where the light will come in from, and I will show you more detailed of that. So Paul Aerospace built the instrument. It's ready to be shipped to Palo Alto in California for them to do integrating it on the spacecraft. So the concept here is the first time NASA is doing this. So since it's in GEO, and NASA decided, okay, we're not going to build a whole spacecraft and put it in GEO just for this instrument. It's similar to ride sharing if you think about it in cars. There's an instrument already, spacecraft already in geostationary. Those, all your telecommunication satellites usually sit in GEO. So the way you get Al Jazeera, HPO, and so on, because they sit in GEO over whatever the designated geographical area they beam their signal to. Those geostationary communication satellites tend to be huge. So it's like you're going to the airport in a minivan and there is only one passenger there, but there is plenty of empty space. So the idea for NASA, there are so many of those, as I showed you, can we find one of them going to 91 West or somewhere around the 100, to put tempo on it, and they found one. And tempo is 1 meter cube. So you could imagine. So here it's going to reside in something like this in GEO. Now, once it gets launched, Intelsat will be the one who operates the instrument. And that's who we will be sending our commands to it. So again, Maxar Technologies is the one who are going to build it. We're going to launch it on SpaceX Falcon 9 rocket. The proposed launch time is summer of 2022. Once it gets launched and so on, Intelsat will take management of it, and we will be doing the commanding and operation from Cambridge here in the US, sending the commands and so on. We have done earlier on, before the coronavirus, in-person kickoff and satellite system requirement review. We completed in May virtually because of the epidemic we're having right now, the host requirements review and the spacecraft accommodation review and ground system design review will be happening later on in September. And all those will be also, unfortunately, virtual. So if we look at tempo and we break it down, so you have the scanning mechanism. So I will show you that in detail and later in more bigger picture. So the scan mechanism will scan the slit. So the light will come in, will hit the scan mechanism, will project it back to telescope optics, to the detectors, to the grating, and you end up getting your spectra. There's the instrument control electronics here, ArAS, which runs the whole, basically, if you think about it, the electronics within the instrument. We built two of those, one that's in the instrument that's going to go to orbit, and one we have in our labs here in Cambridge, US. The ArAS, the instrument control electronics, plus two other racks, big racks, roughly 6 feet tall, high, and 2 feet maybe wide or something, and 3 feet depth. Those, one of them is the instrument simulator, and one is the spacecraft bus simulator to simulate the spacecraft. And we'll use those, all of them, the ArAS, the spacecraft simulator, the bus simulator, as the instrument simulator, as instrument simulator will run the commands on it, validate the commands prior to send them to the spacecraft operations center in the Midwest to send them up to the instrument. Now, and it's here looking at it again, but trying to give you some visual of how things will work. So this is similar to what you saw in the lab. This is where the slit will be, and will be a calibration wheel inside, will open or close to allow the light to go in or not. Now, the slit is fixed like this. So it's a slit fixed north to south. You cannot change too much top and bottom, but the width of it, east to west, you can change it, increase it as big as you want. So now it goes, this is our field of regard. It goes from the Atlantic Ocean to the Pacific Ocean, from almost Cuba to the Canadian tar sand, and to swaps this area roughly 1,200 times every hour. This is the slit. Obviously, it's made here to be wide just for illustration purposes. So if you think of the slit, along the column direction, it gives you the spectra. So that's when you bend your data and you get the spectra type. And along the spatial, you get the spatial distribution. And however, there is a lot of data there, although we have our own transponder. So we have everything we need on the spacecraft. We only get we have our electronics, our transponder to beam down data and so on. We only use their electric power, basically. But even for that, to make the transmission reasonable, so you added some of these frames you take. Now, let's talk about the concept of it. And now all of it is original, the tempo we already built and launched and preparing to launch. So again, as I said, it's imaging grating spectrometer that measures the backscatter sunlight. So the sunlight comes in, hits the ground, radiates back. That's what you see. And it has two detectors, two CCDs, and it's in UV and in Vis. And they go from 290 to 490 and from 540 to 740 nanometer. We use the nanometer units, and the spectral resolution is 0.6 nanometer, and the stepping between these, the width of each one of those samplings or all spectra is 0.2 nanometer. And again, we have two detectors. Technically, you could put as many as you want, but NASA proposal said you have 90 million, make it work with 90 million. So we have two detectors. They are 2D, 2K by 1K detectors. And as I pointed out, the field of regard goes from Pacific to, from the Atlantic to the Pacific. So I show you this one. So you can see this is the field of regard. It goes from the Atlantic. This is how it is, here to there. The spatial distribution, each one of those is 2.1 times 4. So give and take roughly 10 kilometer square. Remember, so now it goes, this scan here, it does, this one here, it goes from this end to this end. It does all of those in 1 hour. And you have 16 hours roughly to observe. That's when it's there is sunlight, and the days when you do, the time of the day when you don't have sunlight, you can do dark rate, you can so do calibration, and many things. You can switch on the diffusers and do many things. But the other important thing is, as it goes from here to there, and as I told you, it goes roughly 1268 exactly steps from this side to this side. So that's actually end up producing 2.5 million spectra per hour. So from here to there, you end up in each hour, it goes like this and comes here, you have 2.5 million spectra. Now, in addition to, this is our normal observing program. We'll go like this and just keep going back and forth every hour. However, it has a mode of special observation. Let's say, as it is right now, there are some wildfires in California. So you might say, okay, come here to where California is, stop. Now keep going back and forth, move the slit over this, basically sit and stare and collect data. For example, if there is any other activity on the ground that you need to observe, special observation, you could do that. Now, how does the spectra look like? So this is the terrestrial planet spectra. So this is important because in principle, this concept, the same concept we propose for tempo in GEO, we had written a similar proposal. We proposed to NASA to build something like it to go on for ExoMars, to go on Mars, but be on around orbit. So in LEO, low, instead of low Earth orbit, low Earth kind of Mars, if you think about it, like just to orbit Mars. So it's the same concept, it's the same thing you will see. These things here might change what you observe, which we will talk about it. But if you look at terrestrial planet like Earth now, and you look what you can see based on the albedo, this is what you will see. So those dashed line, by the way, those are our detectors. So remember I told you we have two CCDs. So those are the two CCDs we have. I have them here. So you can see what element, what species they cover. So if you look at fully cloudy sky, and you measure the backscattered light, this is the spectra you will get. And you will see an O2 here, you will see glycol, you will see the oxygen doublet, the ozone, water vapor, you will see the bromine monoxide, sulfur monoxide, and formaldehyde. However, if you look at Sahara Desert, you know, you're looking over the Sahara Desert and you're measuring the spectra, this is what you will see. See, it's relatively, there is not much lines there comparing to what you see. Now, those, remember, for those familiar with these things, these are observation lines, not emission lines. Now, if you look at vegetation red edge, which is, you know, just vegetation type spectra, this is what you can see. If you look at the clear, there is no cloud, and over ocean albedo you see in here, this is what you will see, and also you wouldn't see too much of any lines. Now, the importance of the retrieval is these lines here that you will see, that what you will get for formaldehyde, for example, here for SO2, for BRO, or for ozone, those are not discrete lines. Those are bands. So you have to look at the whole band. So for retrieval purposes, you have to do radiative transfer modeling. And you take, like, for example, a stretch from here to there, 10 to 15, sometimes 20 nanometer, to decide to fit that, deconvolve it, basically fit it, apply radiative transfer model, put the ring spectra, put any other spectra, and so on. And we'll talk about this to get the actual BRO, for example, or SO2, whatever species or element you're looking for. So now, what are the things we measure that we signed up for under NASA that we must measure, and what the precisions that we have measured? So we're supposed to do from 0 to 2 kilometer, you know, so for all intensive purposes, it's the planetary boundary layer, or basically the surface. So that's the baseline. We'll be doing that in 2 hours measurements. The tropospheric ozone, which will happen at the troposphere, and that's 1 hour. And now for the total ozone, so we measure the total ozone column. So if you're looking top to bottom through the atmosphere, and that's within 3% the required precisions for that. Additionally, we do tropospheric formaldehyde, SO2 glycol, and nitrogen dioxide. Nitrogen dioxide, we have the ability also to separate both the stratospheric and the stratospheric component, and also we can measure optical depth. And I will talk a little bit about this. Now, the mission is 2 years roughly, give and take. It's 20 months with the renewal for 2 years on. And NASA tend to operate this way, but every mission I worked in Solar Heliospheric Observatory was for 2 years, and in the blasting for 16, 18 years. OMI, Ozone Monitoring Instrument, has been around since 2004. And as you can see, 2014, and it's 2-year mission, and it's still running. So NASA will not turn it off as long as it's running, but initially everything is built that you must accomplish your science goal within this period. So that's the idea, is meaning we must measure these things with these precisions and be able to answer the questions, science questions we said we were gonna answer within this period. Otherwise, they won't fund you in the beginning. So now, why is this important? Or granted, as a science team, we are interested in more in the science, how things move along stratosphere, troposphere, how they vary during the day, or variations, so we can, instead of use models, which I will tell you about, how we can use better things of this. However, there are other important component of this. As you can see, the ozone, and I'm not going to talk unless you want me to about how the ozone gets developed. It's 2 oxygen atom connected with the one more oxygen end up to give you the ozone. But you have the ozone in the stratosphere, goes down to the troposphere, and you have the cycle that goes from NO2, water vapor, and so on. So all of these elements, NO2, water vapor, are essential, especially NO2, that works toward, say, the health, the air quality and so on. So it could also provide some understanding the air quality, the health issues that we might have. Volcanic, for example, eruption could also provide enhanced sulfur dioxide with the bromine monoxide sometimes. So though and aerosols. So in addition to basically the science interest, there is also a key air quality component which will hopefully help drive regulations to support air quality and so on. So one of the things we're hoping to do is as I said, with these measurements we can do for the ozone, water vapor, bromine monoxide, sulfur dioxide, aerosols, and or formaldehyde and glycol. From it, actually, we can also derive the UV index and the air quality index. And we're planning to have an app that you can run in smart device like a phone or a tablet. And for your own 2 by 4, like 8-10 kilometer area, you can get the air quality index for that moment. We're going to provide near real-time data and the UV index, so you can determine, is it nice to take a ride in my bicycle, or is it nice to go for a jog or a hike or something like that. Now, we talked about this. Now, why we can do this? From low Earth orbit, these observations I'm telling you about, NO2, SO2, all of them have been done for the last, since 1995 from low Earth orbit with the GOM instruments, Kaimaki and OMI, and our team has been involved with all of these three instruments, actually 4, because GOM was GOM 1 and GOM 2, and those are mostly ESA instrument with big NASA contribution to OMI, and recently there is ARMS, which is a NASA instrument that's similar to OMI. Now this is again, that we have done this, and it's important because our algorithm to do the analysis and to do everything is based on the heritage we have, and that's how we were able to convince NASA to give us the project, is that, okay, we have done this since 1995, we have done it for all of these products or species, as you can see, and we have done it from low Earth orbit. We have a very mature algorithm, and we can actually derive the spectra and get it. It's the only difference now, which we are in geo, it doesn't matter. It's the only difference is instead of looking once per day over one data point, we're going around and seeing it more and more and more. Now, this is just a quick shot here to show, because the instrument itself, the detectors and the actual instrument is built on the heritage, meaning on the knowledge we have from all of these instruments we have. So from GOM 1, which basically lasted, as you can see, from 95 to 2011, Kaimaki 2002 to 12, so 10 years, although all of these were 2-year missions. OMI, which is still orbiting right now, 2004, and the data I'm going to show you for the Middle East are from OMI, and some of the data for US are from ARMS. So GOM 2 stopped working in 2012, and those with either CCD, 2D, 2-array detectors, like similar to us. So AS is based mostly in OMI heritage and ARMS heritage, where the GOM detectors and Kaimaki were linear arrays. And for example, each one of them will cover, like OMI daily. OMI will see Doha once per day, where GOM 1 was seeing it once every 3 days. Obviously for us in US, because we, those all glow LEO, so they can only see the maximum they can see, because just the fact they being in LEO is 1 data point per day, period, that's it. So we have made these measurements, and so far with these instrumentations, we have made more than 10 billion measurements of spectra over the years. So there's significant heritage and knowledge and experience, both hardware, meaning instrumentation, and data analysis and science, for us to be able to get this proposal for TEMPO. Now, I'm showing you here the field of regard for GEO for TEMPO, the American TEMPO, at 91 degrees west. So you can see this is exactly what this is doing. Every hour it will go like this, scan all the way across. This is based in Trop, OMI, and NO2. And oh, I forgot to mention, currently, for instead of OMI, the ESA launched a new instrument that looks daily in low Earth orbit called Trop OMI, and that's the data from it. So this is the data in 2018 monthly average to get this picture. Now, with tempo, you can get this exact resolution, exact image, one image like this, covering the whole field of Vega every hour. So it steps, so this is basically north to south, that's the slit. So that's what the start, see the slit, and keep moving, moving, moving. As I said, you can decide to stop here and keep going back and forth here. You can see the East Coast here. This is NO2, nitrogen dioxide. You can see Mexico City. You can see LA here. You can see much of the pollution. And this is man-made, and some are arguing this is intercontinental drift is coming from through the Pacific from China. But nonetheless, it doesn't matter. It's providing daily measurements every hour, so you can track how this goes. I think this is a still image of the same thing, just to show you the hot spots without having it to go back and forth. So you can see the Canadian tar sands here. Mexico City, we can go all the way down. You have LA here, the East Coast, the West, Midwest, I'm sorry, and so on. So now, obviously, because you're looking in this whole field of regard, so as you can see, the spatial distribution will vary along different pieces in here. So here, looking at the, the pore side, this is when you're looking through the center of it. So if you look at in here, it's at 100 degrees. These calculations are for 92, I'm sorry, for 92 west. The pore site is at 92 instead of 91, but it shouldn't make difference with these things. So you can see the maximum we can have, or the least we can have, is 7.7 in Mexico City because it's coming lower. We can have roughly 10 kilometers overall square. So these, the field of the spatial distribution varies. So it's from Puerto Rico, say, is the bottom here to the bottom on the top. You can see the spatial distribution you can get. Now, and this is another illustration to show you how you can get. So I'm looking over NO2. I believe this is ARMS measurements over Los Angeles, and you can see this image. You can get it once per hour. This one actually took month of generation to get this image. You can get one image like this per hour, and you can see these, obviously the red ones, the high concentration of NO2. Now, this is the same thing. This is Los Angeles LA coverage, so you can see the small red boxes. Those are the spatial distribution, the 10 kilometers square that tempo will cover. And we'll cover this hourly, obviously. Every hour will have something like this detail. Now, I touched on this, but let's go over it again. Why is it important? You said you did this from low Earth orbit for the last 15, 20 years, and we have a great experience in it. Why we continue to do that? Again, remember, low Earth orbit, you can see one data point per day. The spatial distribution is so wide, and I will show you when we come to that. But in here, so here, this is OMI data for 2 days, for June 22nd and June 23rd of, forgot the year, but it doesn't matter. I can look it up. Yeah, 2005. So for June 22, 23 for 2005. So you can see this is over, I believe, Texas. And the other two lines based on GMAC modeling. So it's a theoretical model that looks at NO2 total column density and looks at, which is this one, the darker one, and modeling for NO2 along the surface. So now you're looking at along the surface, and you're looking over the whole column. And you can see you have this model that tells you how NO2 behaves. But observationally, this is model. Observationally and measurement-wise, you only have 2 data points. So, and here they are in imaging. So this the 22nd, this is the data point for the 23rd. So if you have actually an instrument in GEO sitting over Texas, US, we'll measure this here, we'll measure it. I'm pointing with my finger to the screen, which is not helpful. So we'll measure this point, this point, this point, this point, this point. So instead of depending on model, you actually have a data that can actually enforce the model instead of just having models and wave your hand saying this is what I got. So that's why it's important to do these observations from LEO. From GEO. Additionally, one of the other things we're hoping to do, city lights. Many of you have seen Earth from space at night. So you can see the dark of Earth. So you can see just the lights, the areas where it is lit and the areas where it's totally dark. So here, what we have plotted here is we have the spectra for different lighting instruments, say, or sources. So you have fluorescent light, LED light, oil, halogens, and so on. So you can see, and here we have our detectors that we have here in the dotted lines. So you have the tempo, ultraviolet, and the visible detector. And you can see we can cover both of those. So the idea is the hours, because we only can observe for 16 hours when there is sun. Remember when I told you there is no sun, you can do dark rate. Additionally, you can do city lights. So you can measure the city lights and see areas where it's dark or not. And this will be very high resolution, so it will be a lot nicer images than the one you see globally. Granted, it's not a global picture. But nonetheless, in here I give you the website for the project, and you can go see some of our presentations, science, and so on. Now, I'm not going to go too much about this because I kind of addressed it when we talked about all of our algorithms to do all of these data products from unknown to Ozone to ArAS. All of them, we have been doing them. They have heritage throughout all of the 5 instruments I mentioned: GOMAI, GOM2, Schemaki, OMI, and ARMS. And right now, Trope OMI is doing the same thing. It's already been running for a year. So I'm not going to talk about that. Let's move to the Middle East. Let's say, okay, let's build a carbon copy of tempo. However, instead of putting it over US, let's put it over the Middle East. It will be the same thing. I'm proposing the same thing. Exact the same thing. Imaging grating spectrometer will look at the scatter back light that comes back. It's the same detectors. Don't do anything. Why reinvent the wheel? However, for us, it was cost involved. We couldn't add another detector. If you add infrared detector, you can look for methane, measure methane and CO. So again, on the assumption you have 2 detectors, still would work, which we already built. Now, what would the field of regard be? It will be from Djibouti all the way in the bottom to the Black Sea up in north, from Calcutta, India, to Croatia or the tip of Italy in the west. This will produce, again, similar to US instrument, 2.5 million spectra per hour. And because it's closer to the equator, will have better spatial distribution. It will be roughly 8, 1.7 north-south times 4.7 kilometer along the east and west. And you can still do the same thing we've done, the same, because you're using 2 detectors, I said UV, vis, with the same wavelength, with the same spectral resolution and sampling. So the same data products we can still produce, and we have the measuring techniques and algorithms for it. So here I'm looked at OMI, and I plotted OMI over the Middle East. I forgot the dates here, but oh yeah, 2013, I think I took the monthly average for the whole year. So you can see how the Middle East is lit. So you can see the Nile, you can see the ship tracks in the Red Sea, you can see Jeddah, Riyadh, the Gulf. It's impressive, it's significant. Now, if I look at it in static picture, this is the field of regard. So you can see where it goes. This is Italy down here. So you can see it covers everything from India up to the Black Sea all the way to here. So this is Now, taking NO2, just monthly average in April. So taking April 2005, April 2006, 7, 8, and so on, averaging all of those to come up with this picture I have for you here. This, if you put one over Middle East, say in this case, I calculated the calculation, I'm going to show you numbers afterward over Doha, will produce this image once per hour. So you can still see the Delta, the Nile, you can see the chip tracks, you can see Jeddah, Mecca and Medina here. And the interesting thing, I have been trying to get some in situ measurement in there. Although there is Hajj in previous years, there is not much air pollution there. One would think that some of the pollution from Jeddah will go there, extend to the east, but you don't see that comparing to how Jeddah is. Not even, you wouldn't see anything close to what you see along the ship lines in the Red Sea. Now, this is how it moves now. If I, having it sweep, this is the same image, but instead of a still image, it's actually moving across point by point across the field of regard. And this is essential because it can provide us with, first there are other instruments being built and launched or in planning for other parts of the globe, similar to TEMPO. I will mention them later on, but TEMPO is in North America. So this will provide another essential information for the global picture over Middle East. Additionally, as you can see, we have our own share of nitrogen dioxide. This is look at nitrogen dioxide that's man-made. And you can still look for, you can see aerosols, you can look for ozone and everything, even the surface ozone. So this is kind of provide daily measurements and near real-time data. You can get the same thing apply here. You can get air quality index, UV index for every part inside this field of regard, inside this area. So now, similar to the way we looked at it in the States, okay, this is large field of regard. So if I'm look at it in this field of regard and I say, okay, how would the ground sampling area will it change? So again, the pore site, I'm putting it to be 25 north, 51 east, which is over Doha. So you can see 7.87, and it varies, it goes, the worst will be as a 12, which is nothing comparing to the American one, which was 33. This is 12 over Istanbul. Mecca will be 7.9, Riyadh 10, Jerusalem will be 9.7, Cairo, New Delhi. So it will provide significant high resolution, spatial resolution over these areas. Now, and here, this whole thing. So here I'm looking at Qatar. So again, the instrument is sitting over the field of regard, the center of the field of regard is Qatar. So this box here, the big black box here, I hope you can see my cursor, this black box is going to spatial distribution. So this is how big the spatial distribution. Granted, it will see this box once per day, or OMI will see this smaller box here, the other black box, once per day. Granted, we'll see that once per day, but it's a huge box. Where TEMPO will see 16 times hourly, every hour we'll see this small box. This one, this one, this one. So if you extend this, will be divided into some smaller boxes. So you will have the NO2, the concentration, the SO2 concentration, the aerosols, the what do you call it? Oops, why did they do that? Oh, the aerosols, the bromine monoxide, all of the components you can measure, water vapor, everything over this smaller box once per day over Qatar. Now, okay, Ra'id, this is important, this is wonderful, you're telling us all of these things, and why should I care? As I said, again, there are 3 instruments already either built or in planning and more than half built or already launched. So TEMPO, ours is already built, it's sitting in storage waiting for next year to make it to California to be integrated into the spacecraft. Sentinel-4, this is NASA's instrument. Sentinel-4 is being built by ESA. It's proposed to be launched shortly after ours, so it's more than halfway, if not even more, built. GEMS is the Korean instrument that was launched earlier, a few months back actually, was launched a few months back, and they're still doing the on-orbited checkout and commissioning. So as you launch something, you just don't get it, you know, first it takes time to get to GEO, second you have to turn everything on slowly, you do commissioning, you do orbited checkout, you make sure all of the voltages, gains, temperatures are behaving well, then you start collecting slowly science, but then you do validation to confirm this is exactly what I should have. Get the signal before you put the green light and says, okay, we are ready for science now. So they haven't started science yet, they just launched, but this is the Korean. Now, if we take the Middle East tempo and we build it and put it over Middle East, this is where it will sit based on the calculation, based on the data I gave you. Now, everything inside this box, you will see it more than once per day. Okay, everything inside this box, you'll see it more than once per day. The other important thing, now you are part of larger constellation for the whole globe to look at the spatial distribution. The other important thing in this field is, since there is an overlap between Tempo Middle East, I call it Tempo Middle East for the sake of discussion at this point, can be named whatever. As you can see, there's Sentinel-4 named, you can name it whatever you want, but whatever, let's call it the Arab satellite or the Arab instrument will sit here, okay? Now it's have an overlap with the Korean one, have an overlap with the European and with the Korean. Now, what you measure here in the areas of overlap, they should be similar, given the calibration is worked out well and there are no issue in the calibration, it should work out, it should be exactly the same thing you see. So as a scientist, one will be interested in, okay, doing validation between all of these things. Third thing, even if I'm looking at tempo, I'm not gonna interested just to look here. I'm gonna see the whole globe, how it looks, the whole area. So I'm gonna request data from here, data from here, data from there. Any data I get from somewhere else, they have to be on my paper, co-authors. And they have to be referenced. So you can say, this is similar. When I gave you my data, I said, this is OMI's data. This is ARMS data, and so on, or drop OMI, wherever. So if the Korean publish the Arab data, they get to say, this is the Arab satellite or the Arab instrument. And then the Arab names will be on it, and so on. So that's the importance of doing this. And eventually what will happen will be the whole, if you think about it, mostly the Northern Hemisphere will be covered with this, in the assumption this get built, because those are done deal. This is already built, this is more than halfway through and definitely built and money, you know, it's all done deal. And this is already launched. And so those are reality, the three ones. This is not yet. So then you will need one in South America, South Africa, then you have the whole globe in high spatial distribution. So this is an important. However, this costs money. And someone might argue, say, okay, we might not have this. Can you propose something that we can start in baby steps? Right, why do you want to go all the way up there? So, okay, one of the things for us, we depending in US, when we do validation, is you measure things from space and you can measure things from ground, and it doesn't matter, you're measuring the same thing, but it's different direction, if you can think about it. Giving all calibration worked out, you should see the same thing. So one of the things we buying roughly 5 of those, what they call Pandora. They are spectrometers, you can put them on the top of a building, and they come with everything built in it. You just need power and internet connection, and it takes the data and it sends it to Goddard Space Flight Center, and they are across the globe. Actually, they are everywhere in Korea, China, Europe, in US. There's none of them in Middle East. Have been working hard trying to work with NASA and Arab countries to try to put them in the Middle East. What it's made of, it's made of many, you know, as you can see, spectrometer, You put it here, the spectrometer can sit in some isolated box down in the ground, connects with this guy, sun tracker, and it can measure everything basically. It can do 270 to 530 nanometers, so it can do too much of the visible, but it can do direct sunlight. So you look at direct sunshine, you can get ozone, nitrogen dioxide, silver dioxide, water vapor, and formaldehyde. You can do aerosol optical depth and absorption index. You can get the particle sizes, the ozone profile, and NO2 profiles from the spectra, diffuse spectra. So as you can imagine, those roughly, each one costs close to $30,000. I think they like to put them in bunch of threes. You can put them on the top of any building. We have a few of them here and we have one in just across the Charles River from us. We put it at, one at Harvard, and we put one at BU, Boston University. Not at our building, because it's too crowded in the top of the roof of our building. But as you can see, you can put it like this. Now, this is important for multiple reasons. This can give you an advantage. You start the atmospheric process, you start analyzing data, knowing what it is. It can actually provide for a graduate program in atmospheric and in physics. Again, this is identical. We propose similar instrument like this to put it in the rover over on Mars. And unfortunately, we didn't get that proposal to build a smaller spectrometer that sits on the top of the rover and you only connect it with the laptop. So the idea is we'll patch into the rover power and the rover computer system. And it can, it sits like this in 45 degrees, can measure the backscattered light that comes from the sun, actually occultation, direct sunlight, and can do the same thing for Mars. So this is exactly, and you can, we did a concept study for it. We showed that it can be done, and in the end, you can build it and put it on the top of the building to measure Earth until you take it to Mars, or if you don't want to take it to Mars. So this is the same science, the same instrumentation, the same hardware, the same everything you need to look at any other planet. You just have to go there. So before you go there, it's good to build the infrastructure you have, and it's cost effective to do these things. And here it is. So for example, just to give you an idea, this is one that's put in Washington State University, I believe. I think, no, the other one was in Washington State. This is looking at the stuff. I think this is in Dallas. I forgot exactly, but it's looking at the blown air from the Gulf of Mexico down below Texas. And you can see the polluted wind as it's flowing from the ocean, flowing from the land into the Gulf. And you can see the clean air over the ocean, how it is. Remember when I showed you the terrestrial planet type of spectra, you can see the clean ocean albedo. It was the blue one, which nothing in it. And the land is typically tend to be very busy with a lot of spectra. So as you can see here, there is significant pollution is being blown out from, I believe this is NO2, yes, NO2, blown from land into the Gulf of Mexico, where you look at the Gulf itself, there's nothing there. So this will provide significant, knowledge for us, and also build the infrastructure that can down the road lead to actually building an actual space-borne instrumentation. So to summarize, which I kind of said many of these points, but to summarize them, Tempo Middle East, or whatever name one chooses at the end, will allow Arab scientists to be part of a larger pollution and a scientific constellation type of program that's will join the Europeans, the Americans, NASA, ESA, and the GEMS in actually providing high resolution observation of the Earth. And also will definitely establish scientific infrastructure. You will have to train students, research scientists, technicians. You will train them everywhere. Now, the Korean GEMS is which I didn't say, just to let you know, as part of this is scientific infrastructure and the training, GEMS instrument is actually the twin of Tempo. It's identical relatively to Tempo, was built by the same company, Paul Aerospace. They were built at the same time, but the Koreans paid them more money, so they finished theirs first. And their postdocs, we are in their science team, their postdocs are with us, they continue with us. Many of their students did their PhDs with us and went back, and it has been for the last 15 years working with us for them to get to the point where they can launch their own instrument that is similar to TEMPO, the American TEMPO. Additionally, and I pointed that out, you know, since there will be an overlap, so that will provide for a validation and between both GEMS and Sentinel-4, the ESA instrument, the European, will also provide for collaboration in seeking data back and forth and so on. Additionally, if you want to start in a space program, it seems to be the golden opportunity, given that you already have two instruments already built, GEMS and TEMPO. Again, GEMS is similar to TEMPO. It's a sister instrument built by the same company. And you have a third one identical. You put it over the Middle East. Now you already have turnkey, if you want to think of it, experiment that you can put over the Middle East in Doha, for example. That's the center of regard, but cover the whole thing. And this can provide significant opportunities for program, for science. As I said, any paper will publish data from the ArAS instrument, will have ArAS names on it, will have, for example, if let's say if the Qatar is involved in it, will have the Qataris names, will have the ArAS name on it, will have the ArAS name will be in any other paper published by GEMS, Sentinel-4, or TEMPO. So it's a significant collaboration and an opportunity for us as Arabs to try to jump on space. And in here, thank you so much. I think I finished this part of my talk, which I was talking about the geostationary. And these, all of our collaborators, many of the things I have in the presentation are from ESA, NASA, and I use their data, and from Paul Aerospace, Maxar, and Intelsat, and my thanks to all of them for their support, and more to my fellow team members on TEMPO. I'm done with this presentation. I don't know if you would like to take questions now, or should I go to the next presentation that I wanted to talk about the Arab Astronomical Society.
Thank you for your workshop and the informative or the informations that you have. We actually have a lot of questions. So I would suggest that we go through them first from the attendances, and then you can continue with the part about the Arab Astronomical Society.
Yes, please, sure.
Okay, so guys, you can send us your questions at the moment as well if you have, but I'm going to now read to you the questions that attendances already sent. So we have a question from Sultan Al-Khalifi. He actually asked 4 questions, so we will be trying to answer all of them. The first one is, what is the best and accurate web service for forecasting the AOD, aerosol's optical depth in the Gulf countries region?
I don't know actually, and the fact, his question is about observing the optical depth, aerosol optical depth, is that correct?
Yes.
In the Gulf region.
Yes.
I don't know, I'm not aware of any science instrumentations, unfortunately, in the Gulf countries that do something like this. I know that Qatar has worked with KNMI, which is our collaborators, and they are the one responsible for the OMI instrument to get some OMI data analyzed over Doha for the what's the thing coming up for the World Cup. I know in UAE they have worked, I forgot what the name of the center, but I don't think they have their own measurements. I don't know. I know that there are no Pandora instruments in any of the Arab countries or the Gulf countries. I've been trying to work hard with NASA, and NASA is willing to help. Unfortunately, haven't been able to find willing partners to put them in the Arab world. And if you take Pandora, you don't have to be in space. You can measure in situ over, obviously just will be in situ, meaning in the area where you are. So you can put one over Qatar University and you can measure aerosol optical depth there.
Okay.
Yeah, I doubt there is any reliable source.
Yeah, his second question is on AODs as well. He says, how accurate these ODs values for celestial targets near the horizon, knowing that these values of OD are for the vertical column of atmosphere?
Yeah, so, okay, so now when you measure something, you're measuring total column density. So yes, so the only one that will be close to the surface, the horizon, say, or the surface, or the planetary boundary layer, which could go from 100 meters to 3 kilometers, say, is the ozone. There is no other measurements from space you can do close to in situ, you know, I mean, to the along the surface or the horizon. In that case, you will depend on some in situ ground-based observations, which again, we don't have. We can put those, but we don't have. So all of the measurement here is the space-borne, and it's mostly tropospheric, stratospheric components.
Okay, and his third question is, at which wavelength in nanometer Earth atmosphere at the sea level is transparent and less susceptible to scattering the most?
I don't know the answer to that, and I don't know if one can answer that because there are many parameters they can say, think of. The only thing I can say, it depends on the albedo, but we know the albedo over the ocean is very clear. I don't know, I have to look it up, but one thing can calculate the scale height and one can see the scale of the atmosphere, which I'm not going to give you the answer because it's one of the questions.
Okay, his last question on a very softer note, he says, I have an engineering background. I want to study and understand photometry. Are there online courses you can suggest or books that contains exercises where I can test my understanding?
If you can send me email, I can try to find some courses, some books that are in PDF. The one thing I encourage him to look into, and they might have, is edx.org and Corsa.org. They are online, they offer online courses from major universities. I know Corsa, which is, partnered with Stanford University, where edX is with Harvard, MIT, and Berkeley.
Yes.
Corsa offer more space engineering, spacecraft type of things and courses. So he might find something there, but this field is essential for, it's not just like, for example, take Tempo. To build Tempo, we are the science team. We are the science. We said, okay, we want to do this. We want the spectrometer to look this, do that. Besides that, that's it. My job is done. I go to Paul Aerospace, and to tell you, we have to go through many steps just to answer this question, so he can, you know, give him more light about this question, so he can shed more light, so he can understand how important engineering is. So for us, we have to go through many reviews until we get to the point of no return, where NASA can say, okay, we are happy, we believe you, you can do it. So in the beginning, you put the proposal, they do a review and peer review, and hey, guess you win. Now you have system requirement review. So you define the requirements you need. This is what I'm gonna do. And you say, okay, NASA hires or appoints what's called NASA civil employees, which are made of engineers, thermal engineer, electrical engineer, structural engineer, one scientist, one cost to understand the cost, and so on. and they study and they confirm you have done this. Yes, you go to the next step with preliminary design review. The same standing review board does the same thing. So as you can imagine, their engineers are very much involved to know, you know what you're doing, and you can build what you're supposed to build. You can build what you said you were going to build, and you can accomplish the science. So engineering is very wide and it's very open, and I encourage him to look into it.
Okay. Thank you, Sultan, for all your questions. Now we move to Reem at DC. She says, thank you for the great presentation. There is actually a plan to build tempo for Middle East. I think it's very important as pollution is one of the main issues we face in here.
To be honest, I have given this presentation at the American University of Sharjah in a conference there, and we wrote a paper that's already in literature about this. So there is, you can do, Suleiman, I believe I can send a PDF, but it's similar to the stuff I presented. Mm-hmm. So I have been lobbying since 2014 for Arab countries, mostly the Gulf countries, to build something like this. Obviously, that's not something I can build. It requires millions of dollars. It costs us 90 million of whatever, $12 just to build the instruments. I would say nowadays could cost 100, 120, I don't know. You need another couple hundred for launch vehicle and for the rocket, and to put it somewhere. To put it somewhere is easy because there are significant telecommunication satellites that you get all of the TV stations, so you can put it in one. I agree, it's essential that we build one, and if every one of the Gulf countries put, 20 million or 50 million, could be easily more than built and support. Don't forget now, the 90 million we got is to build the instrument and support the science until 2024. Mm-hmm. So meaning my salary and everyone's salary and all of the science and engineers who work on it, and the instrumentation, all that part of the 90 million. So I agree, we should build it. It's important to build it. It will open significant opportunities for us. My dream is to see more Arab names in scientific literature, to see more, to be moved to be, instead of consumers, to be innovative, to build our own things. And it's okay, you have to start somewhere. The Koreans started somewhere. We don't have to invent the wheel. But yes, I hope you guys can carry on the message and to say, okay, can we do this?
We hope that too. Hopefully one of the people attending this workshop or the conference, maybe they will in the future be part of the scientific community that we're looking for. Okay, Reem has another question. She says, how many years do you think we will need to actually benefit from the data collected by TEMPO and GEMS and similar instruments in terms of pollution control?
As I said, looking at OMI, OMI was launched in 2014, still operational. So it could be 10, 20 years until whatever it goes, it disappears. And typically something goes bad, not because the instrument kind of inherit, not the instrument is just, tear and wear. No, it's TEMPO has no lifetime, meaning the mechanisms, when we tested the mechanism for the mirror to move, for the grating to move, they can do this forever. Mm-hmm. They don't just die after X amount of years. The issue is, can something happen in the space environment around it where the temperature rises so much, we do an error in the ground, something like that. Being in GEO, there is less issue of happening than low Earth orbit, where in low Earth orbit, it's prone to charged particles from the sun, like that comes out of solar flare, coronal mass ejections, and so on. So it could live for 15 to 20 years easily. It's only will be the funding. Will NASA keep funding it?
Mm-hmm. So the results that you get are immediate, or do you need to wait for a specific amount of time to actually get a specific amount of data in order to analyze it? I think this is where her question was going.
Yeah, the data can be not immediate, because we as a science team, we are giving a few months to put our stamp of approval. We need to make sure what we observing is correct. There are no, because you build something, you observe it, you know how in the lab it's supposed to behave, but then you put it up there and you get the signal. Now you have to retrieve, to do the retrieval, change it, get the spectra and look at it. Does this make sense?
Yes.
Once that we're ready with that, and I forgot, I think it's 3 months for commissioning, orbit checkout and commissioning, and perhaps maybe 3 months or so for us to check the data to confirm that we are happy with it. The data can be public. Now, OMI data, for example, that's observing daily, you can go right now and get it. ARMS data, you can get it. NASA has moved and ESA a long time ago from having data being holding on the data. Now they are in the public domain. So once the science team that built the instrument decides it's okay, it becomes public and you can get it immediately, and any data that gets produced after that, the next day you can get it, and so on.
Okay, thank you, Reem, for your questions. We have a question from Ali. He says, from your observation, is there a time in the year where air quality is the best compared to the rest of the year? What is this period? And please answer specifically for Qatar's case.
I don't know.
Ali is an astrophotographer. So he's asking because, you know, for him it's important really. The weather and the air pollution,
Yeah.
the air qualities are the most important things and aspects to his photography.
No, I understand. It's very hard for me to answer that for multiple reasons. I only been to Qatar in and out of Doha airport. Besides visiting a couple times UAE for a week or two, I never lived in, and I've been away from the Arab countries since '88. So I've been in US. So even when I visit Palestine, I went once in the winter. So every time I go is in the summer. So I have no idea how the Arab world is in the spring or the fall. So it's hard for me to answer. However, if I want to use it based on what I know here, obviously in the Middle East is different because you have sandstorms, I guess, and more desert rather than vegetation. At least in the northern hemisphere, the fall and the winter tend to be clearer skies. So the important thing for astrophotography, I would say, is to stay away from, which is obvious for him, is the full moon, stay away from city lights. But other thing, he has to depend, unfortunately, in local weather reports, because I have no idea.
And he depends on, as you know, as you said, in Qatar, the weather is very, I would say, extreme in summer, but still Ali gives us great images that he captures. Thank you, Ali, for your question. We have a question from Saifuddin. He says, thank you so much. I enjoyed this. I wanted to understand what is the fundamental difference between astrology, astronomy, cosmology, and astrophysics.
Okay. First, astrology, علم التنجيم.
Yes.
كتب المنجمون ولو صدقوا.
It's a pseudoscience.
It's not a science. Don't mix it up. You bring a coffee and you start reading what's in it. You open that's astrology. Put it aside. That's not science.
Yes.
Astronomy is the study of علم الفلك, the celestial bodies. Now, I'm a physics trained, so I don't really see separation between astronomy or physics. I think of physics is the major field and astronomy is a subsection of it. Now, you study astronomy alone, and again, this is my personal opinion. You study astronomy alone, you might not be able to be very productive in actually understanding things and doing major achievements. Because as you know, all of the physical processes are physics. Physics explain it. Now, what is astrophysics? Astrophysics is similar when you say nuclear physics, theoretical physics, atomic physics, solid state physics. It's a branch of physics that study the astronomy. Now, inside it, there is a high energy. So that's a high energy. There's nuclear physics. There's atomic physics. As you can see, the atmosphere is mostly atomic rather than nuclear or molecular physics, actually. you go to study the gamma ray burst, AGNs, active galactic nuclei, is mostly you have to understand high energy physics, which is same as nuclear physics. Cosmology, they split it and put it alone, which is the study of them, how the universe came to exist. So it's multiple things together, but now they are all one field, if you think about it. Now, a good training, if you want to really do good, to be a good astrophysicist, a good training is in physics. And then from it, because you have to be able to be given a problem and work on it. For example, when I started my career, I worked in nuclear physics, nuclear from space, gamma rays. So I worked in electron volts, you know what I mean, like if units, if you think about it. Looked at gamma rays or nuclear de-excitation lines from solar flares. Then moved down to work on UV, coronal mass ejection, and coronal holes, then moved lower down the line in wavelength. Now I'm working in lower UV, in nanometer, looking at the atmosphere. So the idea is you have to have the solid physics background to be able to do all of those things. Now I have personal interest. I don't say cosmology, but I'm saying in quantum gravity. Well, some people might not say that's even astronomy or astrophysics, because there is significant physics knowledge. So unless you want to sit in a planetarium looking at the planets or two pictures of them, that's astronomy. To understand how things move, the processes, that's physics. Even the dynamics of the planets, all of that physics, classical mechanics. Understanding in black holes is general relativity.
Yeah. Our last question before we move on to the second part of this workshop is from Adana. She asks, based on the quarantine and all the measures we took, did you guys notice any difference in the air pollution? Did the air pollution decrease, or didn't you get enough time to collect such data?
I'm not personally interested in it, but yes, there are significant decrease, and some of my colleagues are actually writing papers right now in our group about the effect of COVID-19 on the pollution. There's significant drop of it, and it's being seen across US, across other parts of the world, but mostly in US. The interest has been. But yes, there's significant drop in pollution.
Okay, thank you, Dana, for your question, and thank you, everyone, for your questions. Thank you, Dr. Rائد, for answering them. And now we will move on to the second part, where you will talk to us about the Arab Astronomical Society.
Okay, thank you so much. I will move to the next presentation.
Okay. And you guys can always ask us questions while the doctor is presenting, and after that we will discuss all of them.
Okay, thank you so much again. So I was giving enough time, so I thought I will introduce something else that I've been involved with, and it's actually the first time I visited the region in 2014 and gave my presentation at Sharjah University. First time I gave it back in 2014 about tempo for Middle East. It led to me meeting some of my other colleagues, Arab colleagues, who had interest in the same things I share, and we end up with establishing the Arab Astronomical Society. And the goal behind it is not to be another astronomical society that's for amateurs. It's more for professional. As I said, we want to build Arab infrastructure that can put the Arab on the scientific map and start some kind of scientific revolution. As part of that is obviously we don't have enough human infrastructure. We don't have enough Arabs who are studying this field, and if they study it, they stay in the region anyway, or they go back. So forgive me if the presentation is in Arabic. I gave it before, so I kept it in Arabic, didn't translate. I'm going to speak in English. If you prefer I speak in Arabic, I can speak in Arabic, but the text is in Arabic. And what do you think? Is it okay to speak Arabic or English? It's up to you.
I think we can speak in English. We already have a translation in Arabic, and I don't think anyone will mind that the presentation is in Arabic or
Okay,
the slides.
sure, absolutely. So,
Thank you.
as I said, we gathered here after providing my, as I said, we did the talk and met a few people. So we gathered in my office in November, in May, I believe May, June 2015, and we submitted a proposal to the International Astronomical Union to host a first Arab school for astrophysics. We won the proposal, and I was the PI, the principal investigator on it, and the lead. So we did that's to hold the Arab School for Astrophysics in Marrakesh, in Morocco. So we did that, and in November of 2016, while we were there, we met again, and as part of us planning for the school, we decided as we saw there is a need to start a scientific organization that's actually built into developing science in astronomy, in astrophysics in the Arab world. So we started the Arab Astronomical Society, which we call it ArAS. AR for Arab, A for Astronomical, S for Society, ArAS. And we registered it back that year in 2016 in Morocco, in Marrakesh, and we were toying around where to register it. Unfortunately, we don't have one country that, we don't have a place that we can register it for all Arabs. Regardless where you go, you have to register it somewhere. And you have to follow the rules of the country. We thought of Egypt, we thought of Lebanon, we thought of Jordan, we thought of UAE. We thought of many places, and every place we thought of had pros and cons. So eventually we end up with Morocco, giving that people who were working on it, or our support that we had at that time, was from Morocco, and it's the only country that can provide us with the flexibility of doing so. So anyway, so the group registered there, and in 2018 we registered it in the United States as a non-profit scientific organization. And again, it's has no funding. It depends on support that we either gain from the International Astronomical Society or any other personal funds. مؤسسة الربان، مؤسسة المجتمع العلمي العربي تحت I don't know what the right word is in English, but led by Dr. Moser Rabban from Qatar, has supported us multiple times in our school and in many of our activities, and we tend to have a very wonderful working relation with Dr. Moser Rabban. But that's about it, the support we have, and we don't have any more support from the IAU, the International Astronomical Society, because they said, okay, you are great, we gave you the support in the beginning to start, but now you should be able to do it in your own, because we don't have money to support everything. So we were supported 1, 2, 3 times, I believe, or from the IAU out of the 5 schools we have held, and every time they give us support, they reduce it, and they said, okay, you should be in your own now. So as I said, it's the group, the organization is based on, trying to gather scientists, build the infrastructure. One of the فاعلين الخير, I don't know what the right word in English, one of the donors, provided a scholarship, منحة المعراج, for Palestinian students to study physics in Gaza Strip or West Bank. So that's for a Palestinian student to study in Palestine, not outside it. Again, I touched on this, but to say it again, so we play, our main goals is to establish a scientific infrastructure community, basically. Provide more support and collaboration between students and scholars and researchers in the Arab world. Provide also some kind of scientific collaboration between Arab universities, Western universities, or other scientific centers across the globe. And one of the main goals, as you know, we didn't advance without actually doing things in Arabic, and وخلقنا القرآن وإنما جعلناه نسيت الآية لا سبحانه وتعالى إن خلقناه قرآنا عربيا لعلكم تعرفون. نسيت الآية، أنا آسف، المفروض عرفتها. المهم، فاللغة العربية مهمة بالنسبة لنا في تعريب العلم الفلك، الفيزياء بشكل عام، وتعريب علم الفيزياء الفلكية. حاليا البورد، الجمعية بتنحكم من خلال Board of Directors. The Board of Directors for 3 years they get elected every 3 years. They don't represent countries, they represent themselves. So, for example, there is Zuhair bin Khaldoon. He's the professor at Qadi Ayad University and the director of Comedians Observatory in Morocco. Myself here, Hassan Drghmawi in Al-Ikhwan University, Ismail Moomin in Canada, Laval University, Abdel Hadi Al-Jabiri in جامعة القاضي عياد، دكتورة سهام الكالي في الجامعة السمائية في الجزائر، هادي سليم المعهد القومي للفيزياء الجيوفيزياء العلوم الجيوفيزيائية والفلك في مرصد حلوان القطامية، ريم فراس في جامعة قطر الإمارات العربية، هالة الجسار في جامعة الكويت. So every 3 years we select a group of us, and Zuhair, myself, Hassan, Ismail, and Abdel Hadi are from the original group that actually started the organization or the society. Original founding members, and the other 4 ladies, they joined us afterward, and some of the members who were with us moved on to other adventures. We provide membership or many membership. We have regular, associate, and student. The regular membership is very simple. You don't have to really be a PhD or anything. You have to have, however, a scientific publication in the last 5 years. You are a regular member, and as a regular member, you get to vote on electing the board, for example, or you get to vote on anything that our society can do. Associate member, any other person, doesn't matter. You could have titles from here to the moon, but you have no research paper published in the last 5 years, you are an associate member. Students can be a student member. So we have those 3 memberships categories, and the membership fees are not that significant, I believe, but anyway, for this year, because of the issue with Corona, we have made it free for all members, and no membership fee, just to alleviate some of the stress and the issues that's come up with due to COVID-19. We have done many projects, and there are a lot of our project we started with. Obviously, the first one is the Arab School for Astrophysics, which in the beginning we used to call it the Arab Winter School for Astrophysics. We renamed it after the second school to be called ArAS School for Astrophysics. Again, ArAS stands Arab Astronomical Society, ArAS School for Astrophysics. And we do this yearly, and the school, I will talk about it when I come to it, but now I'm just want to highlight the projects as a whole. We have Atlas Dark Sky in Morocco, which is Mahmiyat Nujum, and it's the first one in the Arab world, and I think it's counting in the hand in the world. We have ArAS exchange program between students and scholars. So we take students and scholars, and I will talk about this a little bit more. We have Minah, scholarship for students. The biggest one we have right now is the Mi'raj scholarship. We hope that if we have funding or we have money, that we can have other scholarships. The most recent adventure we started with is ArAS or IAR Astropytes. And what is that? That is, so many of you are familiar with Astropytes, which actually, kind of small, short what you call description or writing of scientific papers in all of astrophysics written by students and from papers that have been published. So the students summarize it and puts it, and they publish it in many languages. It started with English, and there is a current one in Spanish, one in Portuguese. There is one in apparently in audio function. So we made an agreement with them that we would like to be the official Arabic version, and we called it ArAS for the Arabic. So again, in order for you to write in this, it's up and running right now. We had significant feedback and support, and many articles have been translated. And we continue to increase this. We just started in this couple of months, I think it's a month ago or so we started. We hope to increase the number of articles, and in addition, as we translate articles, we're building a dictionary, mustalahat, where we put them the words that we either unfamiliar with or we didn't know, or we made an intelligent decision what the translation should be. We put it in, and we hope one day that we will have a large or add to the existing dictionaries of astronomy and astrophysics. Now talking about the schools. So the schools, the concept behind the school, the first school we held in Marrakesh, and here they have a picture with all of the students and that who came, and here Dr. bin Khaldun, I think here I am. I was younger and have more hair. Ismail is here. So the school concept is the following. In the beginning, when we started it, it was obviously we just starting. So we had 4 scientific topics, which was too much. We realized that. The goal is, okay, there are not very advanced or instructions about astrophysics in the Arab countries, or the students, the countries that have astrophysics or have PhDs, like Egypt, Morocco, Algeria, and Lebanon. They might not have students enough knowledge of what I should study, like the question we had, what is radio astronomy? What is cosmology? What is this and that? So the idea is, okay, we need to build the infrastructure. We need to bring people from the outside the Arab world and select a student from every Arab country. So the school is basically one student from every Arab country. We pay for the students to come in from his country. We pick him up from, we pay for the airplane ticket. We pick him up from him or her from the airport to the place of where the lectures will be. We pay for food and housing for the time, all of the school time, the period. And the host country can have up to 20 students. And obviously we don't have enough funding to have more than 1 student or 2 maximum from Arab countries. The first school we had close to 58, more than actually, I think 59% of the students were females, and the percentage has been like that. Close to 60% of all of the participants are females, which is very great. We had students from across the Arab world, minus the countries that unfortunately had in a war. We had from Saudi Arabia, United Arab Emirates. Unfortunately, we didn't have anyone from Qatar. We had from Kuwait, Iraq, Yemen. We had 1 student. We had Sudan, Egypt. We had Tunisia, Morocco, Algeria, Palestine. We had from West Bank, Gaza Strip, Lebanon. We didn't have anything from Syria or, I think Syria. The Gulf country, only United Arab Emirates and Kuwait so far. And Saudi Arabia, we had one of the students, I think this is him, in the first school. In the second school, we held it in Jamiat Al-Akhawain University in Afran. Now, the instructors come from the outside world, from the outside the Arab world, not outside world, because there's only so far this world that we are aware of. But so we, in the first school of astrophysics, and the one in Marrakesh, we had from Oxford University, Paris, Nice, Oxford and Harvard University. In the second, we had from Harvard, this guy here, Andy Sangiorgi. He's one of our great supporters. He supported us for $5,000 for this school because we were denied funding in this school here. So he literally supported the students to come over. So we bring students from everywhere. We had from Denmark, one of the professors to come. We had Torino Observatory, and so on. So the idea is we ask these instructors to come using their own funding, either from their own pocket or their institution, but we ask the host country, like what happened here, is to provide housing and food for everyone, just because we don't have funds to provide for everyone. The next school, we held it in Lebanon, Beirut, in the American University of Beirut. We had support from Kuwait and Muassasat al-Rabban. And as I said, we had people from Italy, professors from US and India to talk about it. As we move forward in the second school and third school, we were more understanding, and we learned a lot. So we decided, okay, we're not just going to offer any program. We will come to the host country, say, okay, you the host country, what would you like to have? We will have 2 scientific programs or subjects, say. You select one, we select one, and you select whatever you want. What do you need help with? So, for example, nuclear astrophysics, the American University of Beirut, that's what they're interested, so that's what we focused on. Next year, we went to Qattamiya in Egypt. And in there, they have a Qattamiya, which is 1 meter telescope. So they were interested in actually doing optical spectroscopy with the telescope. So we invited Belgium professor, Harvard came in, and the Moroccan colleagues, which they have advanced with the Comedian and TRAPPIST telescopes to provide more support. So we decided we are not going to select anything, you select, we are here to help you. So as part of that, we started, and we had started it earlier on, which I will come to, but we had 2 students come in, Fatima Sha'ban and Wasim Sayed. They magister students, master students, and we offered that, okay, at the center, we can support them. So unfortunately, they didn't come in, but you know, we did things remotely. So they were, Wasim just defended his master thesis in AGNs, active galactic nuclei, and Fatima, she's working with me and another professor from Chandra X-ray Observatory, working on supermassive black hole. I meet with her, we meet with her, both me and Anita, every week, once, you know, for 1 hour or 2 weekly, to discuss her research and so on. So that one of the programs we started is to say, okay, let's say Qatar University can be the granted institution that will give the master or PhD degree, but we can provide the professor and the research from here, and we can be the middleman. So these are the posters for the 4 schools so far. The 5th one is being held online. We were going to go back to Egypt, but unfortunately now everything is online. And you can see the supports we have been getting has been increased from the beginning toward the end. Now, where are our students? So from the students who have participated in the schools so far, we have Fnan Al-Ustad from Gaza. She's one of the students who came from Gaza. She finished her master's degree in Leeds University. Maysa Yazidi from Tunis. She's in Padua University. Mahmoud Awanshra, the first one, came from Birzeit University. He's in International Center for Theoretical Physics in Tripoli. Jamila Shukar, she came here, stayed at Harvard for 1 month. She has a paper I will highlight about exoplanets. She's doing her PhD. She and Abdurrahman Sapuko, both are PhD students from Morocco, came here and spent some time, a month each, at the Center for Astrophysics in Cambridge, and Dalal Al-Yusufi in Le Pens. Now, again, it's no big deal. I talked about it. We were supposed to have him be in Egypt. Unfortunately, we're doing it on the internet. The school is going to be from the 16th to the 26th of October online. We have done other programs in addition to the dark side, the exchange program. So we had gotten IEU grant from the IEU, International Astronomical Society, to teach physics high school teachers how to teach astronomy in Palestine. And we did this in 2019 with collaboration with the Palestinians there and the Ministry of Education. The Ministry of Education put a unit in grade 9, a unit about astronomy. So the idea was we will train these high school physics teachers how to teach the astronomy. We co-sponsored the 3rd International Gathering for Science in Palestine and MIT here in 2019. We took a group of researchers from Qattamiya to Canadian to train them prior to the school in Egypt. We organized site testing for a workshop. As you know, I don't know if you are aware, but Egypt, the Qattamiya Marsad or Observatory have got funding from Egypt to build 6-meter telescope, and we are working with them to do site testing. We did a conference on that, a workshop. If you are interested in working with us, we have an MOU for collaboration. Please reach out. Now for research collaborative, we have had a few people come. This is Dr. Randa Asad from American University of Sharjah. She has came here in 2015. She has been coming. She just left actually, unfortunately. After she got stuck here because of COVID, she comes to the center. She has been working on clusters, galaxy star clusters. This is Dr. Suleiman Baraki, Ismail Mu'min. This is myself, and this is back then. This is us in one of the telescopes. This is back then. It one was built. It was the oldest telescope in US. It's in the center here. It's not operational. Back then, it discovered the 8th moons of Saturn back in the 1900 something. So this is Abdul Rahman that I told you who came here. Me, myself, Andy, and Justin. They worked with him on his paper on exoplanets. This is Jamila, myself, and Andy. We had 2 undergraduate students come from United Arab Emirates, Falah and Miriam. Miriam is Emirati, she's Palestinian from Gaza. They work with Randa Asad and me and myself. So what we have done, Jamila Shukur just published a paper in about exoplanets, and it's one of the major papers. Farah Balaha, which is one of the Farah and Miriam, both with Randa, published a paper in a scientific conference, and Randa has published. This is all of the research that's been based on the collaboration between the ArAS, Arab Astronomical Society, and them. Abdul Rahman is working with them. People in a paper right now has been submitted for currently, and I believe it's in review. And Sarah Seeger is one of the prominent MIT professors, and she's one of the co-authors with Abdul Rahman, and she's an exoplanet expert. Wasim Saeed has, as I said, submitted his and defended his presentation on active galactic nuclei. Fatima Shaban is working with me on supermassive black hole. So this is a picture of Jamila with her paper, as this is the citation for it, and this is how it was pointed out or referenced in the Moroccan media. And this is the flyer for the science in Palestine. This is the ArAS, Arab Astronomical Society, was a contributor to this, which is to was held for the 3rd year in US in MIT, and to just point out the struggle of doing science under the occupation. And what else? We always seek to look for other collaboration between us, Arab, and international organizations. So please, if you would like to work with us, let us know. Again, please join the society. There is a room for everyone. We want to build our countries and make sure that we are making the science and defining it rather than just consuming it. If you have any information, you can, or if you have any questions, please either talk to Zuhair or myself.